I want to introduce to you a concept known as first principles reasoning. In today's world, in 2026, with automation and AI taking over and increasingly and rapidly expanding and growing in complexity and capability, it came to my attention that the only real way to stand out is to become an expert in a specific niche area of your choosing. That is why in this video, we're taking a slightly different approach and we're looking at a new paradigm shift that will enable you to think critically and deeply in order to achieve this desired outcome of expertise. I'm going to apply it to cybersecurity, but you can apply this paradigm into any field of your choosing. It's very important, so hopefully you enjoy this video. Mastering cybersecurity via first principles. Aristotle. He is essentially the godfather of this term. Aristotle believed that you couldn't truly say you understood anything until you broke it down into its first causes or primary facts. In his work on physics and metaphysics, he argued that searching for these foundational truths was the only way to clear away human assumptions and cultural conventions. Elon Musk, the richest man in the world currently, he is a huge advocate for first principles. Highly recommend watching YouTube videos where he explains it in action. And thirdly, Reed Richards, the smartest man in the Marvel universe. He uses first principles by treating the laws of physics as variables rather than boundaries. There's a scene in the recent Fantastic Four movie where he deconstructs a massive world-ending threat into its baseline truths and then reconfigures a solution from there. So, just to introduce this new concept, think of it as a paradigm shift. Most people learn cybersecurity backwards, memorizing rigid tool syntax and compliance checklists, and inevitably fail when confronted with a novel attack. This happens to me as well. This is concept that I'm trying to implement and improve on as well. So in contrast, elite hackers and security architects rely on first principles reasoning, stripping security down to its foundational truths of physics, logic, and core network protocols. By understanding how systems actually operate at their lowest level, rather than just learning how to audit them, you can anticipate vulnerabilities before they are ever discovered, master new technologies instantly, and think far outside the standard security sandbox. So what is first principles thinking in cyber? Reasoning by analogy versus first principle. Reasoning by analogy is like navigating a foreign city using someone else's outdated tourist map. You copy their footsteps, assuming their paths are safe, efficient, and still relevant. In security, this looks like blindly inheriting legacy tech stacks, adopting compliance frameworks as a substitute for actual protection, and buying standard security tooling simply because it's industry standard. First principle thinking, by contrast, throws the map away to study the literal topography of the land. Instead of asking what other companies are doing, you break the environment down to its raw, unalterable realities. The exact data types you hold, the precise pathway they travel, and the physical architecture of the hardware hosting them. While analogy leaves you vulnerable to the blind spots of the crowd, first principles allows you to engineer custom defense strategies derived straight from the immutable laws of your unique system. So the core axiom, if there's anything I want you to take away from this video, for cybersecurity in particular, it's this. In cyber, everything eventually distills down to three fundamental truths. We have state, data at rest, in transit, or in execution. Logic, code that dictates how state changes. And identity/permissions, who or what is allowed to alter that state or logic. And here's a little diagram, just for your reference. So there's three main pillars to learn. The first pillar is deconstructing the system, the reverse engineering mindset. Stop looking at the user interface, look at the protocol. Relying on a vulnerability scanner to find flaws is reasoning by analogy. You are hoping a known pattern matches a known signature. First principle thinking forces you to drop the wire, to the wire rather. Instead of asking which button triggers the API exploit, you might ask, how is state being maintained? Is it buried in a stateless HTTP header, a stateful cookie, or an ephemeral token? What happens at the transport layer? If a packet is fragmented at the TCP handshake level, how does the firewall reassemble it versus the target operating system? When you understand that the exact RFC specifications of a protocol, you don't need a hacking tool to tell you a vulnerability exists. You can see the logical flaw inherent in how the system handles raw data. In networking and cybersecurity, RFC stands for Request for Comments. RFCs are official numbered documents that lay out the foundational rules, specifications, and protocols of how the internet actually functions. They are authored by engineers and computer scientists through the Internet Engineering Task Force. When you look at the security from a first principles perspective, an RFC is the ultimate source of truth. It defines exactly how a protocol like HTTP, TCP, or DNS is supposed to handle data at its lowest level. Examples of famous RFCs is the Internet Protocol, Transmission Control Protocol, and Hypertext Transfer Protocol. The why. Chain decoding vulnerabilities. To illustrate the difference, let's look at how a standard flaw is perceived through both lenses. The analogy view. SQL injection means I type this into a login box to bypass the password screen because that's what the cheat says to do. First principle view, the system fails to strictly segregate user data from execution instructions because the application takes an untrusted string and concatenates it directly into the interpreter's command passing logic. The SQL engine's Lexa misinterprets the data boundaries, rather. It treats a user-supplied string as an executable conditional operator, altering the intended logic flow of the database state machine. Pillar 2, threat modeling from the ground up. So first you deconstruct, then you go from the ground up again. Instead of using generic threat lists like standard top 10 templates, build custom models by asking the fundamental questions. What is the asset, the ultimate source of truth value? What are the absolute entry points? Attack surface reduction. What assumptions is the developer/system making? And vulnerabilities live in unverified assumptions. So an example for the authentication is if a system assumes a JSON web token is safe just because it's signed, a first principles thinker asks, what component actually validates the signature? Can I force it to use the none algorithm? Where is the cryptographic trust rooted? The third layer is outsmarting the tools. So for offensive, pen testing / capture the flags, while conventional penetration testing relies heavily on superficial abstraction layers using automated frameworks and vulnerability scanners that fail the moment a target introduces minor variations like custom input filters or memory mitigations, a first principles attacker bypasses these tools entirely to interface directly with the system's baseline constraints. Instead of operating on a binary assumption and rigid signatures, they analyze raw hexadecimal network responses, debug application memory registers, and dissect CPU instruction sets. Because they understand the exact logical and mathematical boundaries of the underlying technology, they do not rely on pre-written exploit scripts. Rather, they manually manipulate core system primitives at the byte level to force the system into an unintended state. Defensive blue teaming architecture. Conventional defensive security operates reactively by chasing superficial indicators of compromise, like file hashes and IP addresses, creating a fragile perimeter of signature databases and checklists that malicious actors can easily bypass with trivial code alterations. In stark contrast, a first principles defense focuses on the irreducible execution pathways an attacker must utilize to achieve their objective, regardless of how the threat is disguised. Instead of trying to detect millions of unique ransomware variants, this approach monitors the highly finite set of the core operating system API calls required to open, read, encrypt, and write data, allowing defenders to neutralize entire classes of exploitation permanently and render surface-level mutations completely irrelevant. So, the practical blueprint, how to train your brain. The first step with first principle reasoning is the why rule. So never type a command or configure a policy unless you can explain exactly what it does to the underlying operating system or network packet. Step 2 is build it to break it. Don't just learn how to exploit a buffer overflow. Write a vulnerable C program, compile it, and look at the stack in a debugger. Third step is to strip away the abstraction. Regularly drop down a layer. If you use Python, understand C. If you use Linux tools, understand the Linux kernel and system calls. Strays. Conclusion, the final call to action. As artificial intelligence accelerates in capability and displaces traditional technical roles, The professionals who survive and thrive will be those who cultivate elite, unassailable expertise in niche subject matter. This caliber of mastery cannot be achieved by skimming the surface of existing frameworks or copying established paradigms. It demands first principles reasoning. Only by dismantling systems down to their irreducible, fundamental truths can an engineer construct novel solutions that automation cannot replicate, securing an indispensable position in a rapidly evolving technological landscape. Thank you. For those watching this video, I wish you the best of luck in the future in your technology career. And in this world of uncertainty with AI, I really hope that you take this into account and use first principles reasoning to really think deeply about your subject matter and get passionate about what you're studying and what you're implementing. Thank you very much. I'll see you in the next video.